So not all nuclear reactions are the same. They actually give off three different kinds of radiation. Sometimes they give off alpha particles or alpha rays. That's the Greek letter right there for alpha. Sometimes they give off beta particles, and sometimes they give off gamma particles or gamma rays. And so those are the Greek letters there. And so alpha, beta, and gamma is typically how we refer to it. And again, radiation just means, right? It shoots off an array of light, so to speak. So it just moves off in a straight line. That's all radiation means. When you throw a piece of paper through the air, you could, I suppose, describe it as being radiation if it moves in an array or in a straight line, although I don't think paper is going to give you cancer. So there was a very nice experiment done 100 or so years ago, and it took the radiation from these decaying atoms and it passed it in between two plates. And what we find actually is that the radiation bends in one of three different directions. And so some radiation actually bends ever so slightly towards the negative plate, and these are alpha particles or alpha radiation. And because it bends towards the negative plate, we know that the radiation itself must be positive, and because it only bends by a very small amount, we know it must be relatively heavy. So that we can contrast that to beta radiation, and beta radiation, I'm going to draw in green, it goes right all the way like that. And we know that it must be negatively charged because it's attracted towards the positive plate. And we can also see that it bends by an enormous degree, so it must be quite light, right? So it must have very low mass. And there's a third kind of radiation that basically just passes straight through, and it is completely unaffected, and this ends up being the gamma particles. And the gamma particles actually have no mass whatsoever. They are essentially the equivalent of very high frequency light, and they also have no charge whatsoever. So those are the three different kinds of radiation, and let's discuss them here on another slide. So a lot of experiments were done, and we ended up showing that the alpha particles were actually the nucleus of a helium-4 atom. So it's a helium-4 atom nucleus, and if you remember, that consists of 2 protons and 2 neutrons. So that's why it's got a positive charge. So it is extremely heavy because these things here add up to 4 atomic mass units. And if you compare that to, say, a beta particle actually corresponds to an electron, at least the most common kind does. So we're going to write that as an E-. And if you remember, its mass is essentially 1/2000th of an atomic mass unit. And the gamma particle, it turns out, corresponds to a photon, or a particle of high energy light. So it is a particle of very high energy light. And if you've ever had an X-ray, you should know that gamma particles actually have even more energy than X-rays do. It essentially has a mass, or at least a rest mass, of 0, so it weighs absolutely nothing at all. And the speed of these things is pretty incredible, actually. The gamma particle moves at the speed of light, so if c is the speed of light, which is 300 million meters per second, then the gamma particles move at the speed of light. Whereas a beta particle moves quite fast, actually, about 9/10ths of the speed of light, whereas the alpha particles move quite slowly, only about 1/10th the speed of light. And in terms of penetration, the alpha particles are blocked quite easily, so they're blocked by things like paper or skin. So the alpha particles, really, if they come into contact with your skin, they might burn your skin, but they're unlikely to penetrate through. However, if you breathe them in your lungs, of course, there's no layer of skin protecting you, so they're quite dangerous there. However, if you look at beta particles, the beta particles are harder to stop. They are blocked by several inches of wood. I guess not just wood, actually. Heavy clothing will do it. Thin sheets of lead, large sheets of glass, they'll do it. So it has to be a little bit more substantial than something that you would need to block an alpha particle. Whereas gamma particles, you need extremely thick sheets of lead to block. So they're blocked by incredibly thick sheets of lead. They're very hard to work with. Because they're incredibly hard to stop. So we can see that these gamma particles, right, carry a lot of energy. They're very hard to block. We can use them to kill tumors. They basically just move through all the intervening tissue and just tear through the tumors. Beta particles can be used as well. They don't penetrate as far, but they'll penetrate through a limb, let's say. Whereas alpha particle radiation, they might be able to sort of destroy tumors on the outside of your skin, but you'd have to kind of peel off your skin a little bit, I suppose. So very gross stuff.